So this is the review session for EGME 407 for spring 2022 for the first midterm. All right, so I checked the poll, and the winning topics were 2D conduction and thermal circuits, right? And so I plan to go through both of them today for the next hour to help you study for the midterm. Okay, so let's go and get started. And so let's start with 2D conduction. All right, so the idea with 2D conduction is, kind of what it sounds like from the name. And so it's basically conduction that takes place in multiple dimensions. Okay. Okay. So this is significant because up to this point of what we covered in the class, we had only covered just one-dimensional conduction, right? And by one-dimensional, I mean there's only one spatial component, okay? And so in multiple dimensions, that means we have conduction that happens in components that take more than one, okay? And so to put this in kind of Cartesian speak or Cartesian coordinates, this would mean that our conduction or temperature distribution is a function of multiple variables. Okay, and so for instance, if we look at 2D, then it would be a function of x and y. Okay, and so the motivation behind this was that the heat equation that we normally solve is actually a multidimensional heat equation, right? And so the one that I kind of showed you, that we've seen before in class, has only been the one-dimensional version. But if you write out the entire heat equation, it would look something like this. Okay, so we'd have derivatives in all three directions. Okay, so I'm gonna write the most generic one here. Okay. Right, and we even have time as well. Okay. So normally, when we're solving these equations in 1D, we only have to worry about one of these at a time. Okay. And so we had just one spatial derivative, and we ignored all the other ones. Okay. And then for heat equation problems, we also ignored the unsteady term as well. Okay. And so because of that, we could transform this into a regular derivative. Right, so we have d squared t dx squared, right? And then thus we could treat this as an ordinary differential equation, which we can simply integrate and solve. Okay. But that's not the case, in general, right? So in general, we have multidimensional phenomenon, and so we have to account for all of these things at once. Okay. The problem with that, and the problem with this equation, is that it requires a very strong mathematical background in order to solve the whole thing. Okay. And in particular, you have to know how to solve partial differential equations, right? Because we're going to have derivatives in x, derivatives in y, and sometimes even derivatives in z. And so you're going to have to solve all those terms exactly. Okay. And so solving PDEs is way beyond the scope of this course, and in fact, I would argue it's even beyond the scope of an undergraduate degree. Okay? You don't really learn how to solve PDEs until you get to graduate school. In graduate school, you would learn first of all, analytical methods for solving such equations, or you might even learn computational ones. But for this class, for all intents and purposes, you can assume that we're just not able to solve this equation. And so instead of solving the heat equation, what we do is we kind of use an approximate method. Okay. And that approximation allows us to perform, thermal analysis in 2D and 3D situations, without having to solve the heat equation. Okay. And the way that approximation works is something like this. So even though this equation right here, this large, partial differential equation, normally that's too hard to solve by hand from scratch every single time, but people have done it before. People have solved this equation before. Not only that, is that there's also been a lot of experiments that have been done centered around this equation to quantify, the amount of heat that gets transferred in multi-dimensional situations. Okay. Okay. And so what we can do is we can say, let's leverage those solutions. And so if someone has already solved this equation before in some common situations, so not all of them, so that would be way too much to do. But in some situations that are fairly common, we do have solutions for these. And the reason we can do this, and this is kind of beyond, what I would expect you to know for this class, but in case you're curious, the reason we can use other people's solutions and apply them to ours is the fact that this equation right here, this multidimensional equation, even though mathematically it is a monstrosity to solve, at the very least it's a linear equation. And so linear, the reason I can call it linear is because we don't have any temperature squared terms. We don't have any spatial terms squared except for the derivatives, right? And so mathematically, when you have linear equations like this, they're usually a lot easier to work with. Okay, and you can build a lot of approximations off of linear equations as well, right? And so that's part of the reason why we can do what we can do, is because this equation is linear. But if you compare it to an equation like the Navier-Stokes, Navier-Stokes is very famously a nonlinear equation, and so we're not able to do that. But that's just kind of mathematical trivia. You don't have to know that for this class. Okay. And so basically, the approach that we're going to take is we're going to leverage the solutions that other people have done to solve our system. So now the question is, how do we do that? Okay. In other words, how is this information stored, or how is this information encoded so that we can actually use it for practice? And so the way this information is stored is through a factor called the shape factor. Okay. Right. And so our equation looks something like this. And so if we have a multidimensional situation, and we want to compute the amount of heat that gets transferred through that situation, I should be a bit more clear here. So I think I've kind of loosely said, heat transfer just by itself, but in particular, we're looking at heat transfer rate. Okay, this is going to be equal to S. Okay, S being our shape factor, multiplied by K. K is our thermal conductivity, multiplied by the temperature difference between 0.1 and 0.2. So S here is shape factor. K here is thermal conductivity. Okay. Delta T12 here is the temperature difference. Okay, temperature difference between two locations. Okay. All right, and so pretty straightforward. And so if we rearrange this equation, we can make it look kind of like a thermal resistance equation, which we'll go over later. Okay. And so that's just another way to write this equation that gives us the same thing. Okay. All right, and so obviously, the thing here that's most important is the shape factor. Okay. And so the question is, how do we compute these? Okay. Okay. And so these shape factors that show up here have all been tabulated in the past. Okay, and that's the table that you see in the notes, right? And so the notes, I think it's page 15 of the of lecture note 03. You'll see a table which lists a lot of these situations. Okay, it doesn't list all of them, and so if you go to table 4.1 in the book, in chapter 4 of the textbook, you'll be able to see the fuller table with all of the shape factors. Okay. Okay, and so the way that you basically do this is that you look at your geometry. Okay, so step one, look at your problem geometry. Okay. After you look at the problem geometry, the next step is to find the entry in the table that matches this geometry. Okay. And then three, once you find the entry in the table that matches your geometry, use the last column to compute the shape factor. Okay. Okay. All right, so that's the that's the methodology. This is what you would do in general. Okay. For the exam, I know that's the thing that's on everyone's mind. The exam, I don't expect you to know this table or to write it down in your sheet of notes, because the exam is closed book, but I do allow you a sheet of notes. Okay. And so if I do give you a 2D problem, I will give you the formula for the shape factor. And so you can kind of skip steps 1 and 2, and then you just basically plug in for step 3 right there. Okay. Because it's a lot of information in the table, and you only have one sheet of notes, and so I'd rather you use that space for more productive needs. And so writing down some of the other units, because if you try to put this table into your cheat sheet, it's going to take up so much real estate that you're not going to have room for anything else. Okay. But I did want to do an example, and actually I'm going to do the example that we didn't get to do in class. That's in the notes, just so that you can kind of see this in action. Okay. All right. But that's basically it. And so as soon as you have the shape factor, right? As soon as you have the shape factor, you can basically treat it as if it's a thermal resistance, and then use that to compute, the amount of heat transferred in that situation. Okay. Okay. And of course, because thermal resistances was the second most voted topic, we'll cover that one after this. Okay. Okay, so let's go ahead and do the example. Okay, so I had so in the class, I think we did one example together with the pipe that's buried, but there's one more. Okay, and so I'm gonna go ahead and do that example here, just so that you can have it for your study. Okay. Okay, and so in this situation, we're going to solve for the heat transfer that's coming out of a box. Okay, so this one, I really like this one because it's it combines 2D conduction, but it also has some 1D planar conduction as well. And so I think it's also kind of a good segue for us to go into talk about thermal circuits after this. Okay. Okay, and so in this example, we have a cube. Okay, and what I tell you in the problem is that the cube here represents some kind of furnace, and so the furnace here is in a cuboidal shape. Okay. Okay. And so the cube has a side length of 50 on each side. Okay. Right, and so it's 50 by 50 by 50 centimeters. Right, and is made of a type of material called fire clay brick. Okay. And so the thermal conductivity of fire clay brick is 1.04 watt per meter K. Okay. All right, so the furnace has a thickness of 10 centimeters. Okay, so the walls of the furnace are 10 centimeters thick. Okay. Let's see, the inside of the furnace is 500 degrees C. Okay. And the outside of the furnace is 50 degrees C. Okay. And so under these situations, let's compute the heat loss from the furnace. Okay, so let me go ahead and draw a picture for this. And so we have a cuboidal furnace. Okay, and so it looks something like this, where each side of the furnace is 50 centimeters. The inside of the furnace is 500 centimeters or 500 degrees C, and the outside of the furnace, so we'll call this TS, is 50 degrees C. Okay, so we have a difference of 500 to 50 going from the inside to the out of the furnace. Okay, and so let's kind of visualize what's going to happen with the heat transfer rates, you know, in this situation. And so if you can imagine, you know, you have this box that's a furnace, right? And the inside walls of this box are held at 500 degrees C. Okay, heat is going to be radiating out across all the sides. Okay? Okay. Okay. That's because we have a 2D case. Okay. And so there's three types of structures that the heat's going to pass through. Okay. And so first of all, we're going to have a large portion of the heat passing through the walls. Right. Right. I'd say that's the majority of the heat that's going to come out. We're going to have some heat that passed through the edges of the box as well. Okay. Right. And so whatever heat that passes through this edge right here. And we're also going to have a small portion of the heat pass through the corners as well. It's not going to be much because, you know, the corners are really small, but we do have to take into account because this is a multi-dimensional situation. Okay. All right, so let's count how many walls and edges and corners that we have on this cube. And so for the walls, we have basically just a cube, and so we have 6 sides to this, you know, to the structure. Right. In terms of edges, we have 12. Right. So if you count the number of edges on the side of the cube, you get 12 there. Right. And then we have the corners. And so for the corners, we have 8 of them. Okay. And so let's use this information to compute, you know, the amount of heat transfer that's going to come out. Okay. Because this is a multi-dimensional situation, we have Q is going to be equal to S times K times delta T. Okay. If we plug in for K and delta T here, we have Q is equal to S times K. K is 1.04 watts per meter K. Okay. And then the temperature difference here is just 500 minus 50. And so this is 450 degrees C, right? And so we have K and we have delta T. Okay. And so the only thing we need now is the shape factors. Okay. And for this box, since we have just one box, it's just going to be one shape factor. Okay. Okay. All right. So, you know, I broke this down into the different types of geometries on purpose. Okay, because then that's going to allow us to compute each of the shape factors individually. Okay, so the walls are going to have a certain shape factor, the edges are going to have a certain shape factor, and the corners are going to have a certain shape factor as well. So we're going to compute all of them individually, multiply by how many of these that we have in the system, and then just add them up at the end. Okay. Okay. So let's start with the wall. And so the wall is, I think, simpler than you think because it's something that we've seen before. Okay. And so the wall can be modeled as simply a planar wall with some thickness. Okay. So it looks something like this. Right. And so this we actually don't need any shape factors at all because we know what the resistance of this is. And so the resistance for this is simply going to be the conduction resistance of a planar wall. And so the conduction resistance of the planar wall is going to be L divided by Ka. Okay. All right. And so how do we get the shape factor from this? So the shape factor, you can see here that the shape factor is, or this quantity right here is S times K, right? And so the resistance for 2D case is equal to 1 over S times K, right? And so if we take K out of both of these, because that's going to be shown in both, we can see that the shape factor is equal to 1 divided by the resistance, okay? Minus the K, okay? Right. Factor, let me add this, okay? And so it's going to be K times the resistance right here, okay? And so the resistance here is L over Ka. And so if we multiply that by K, that's going to get rid of that. And so the shape factor for our planar wall here is just going to be A over L, okay? And so we can compute that for, for our particular case, because the cross-sectional area here is just going to be 50 centimeters by 50 centimeters. So that's going to be 0.5 times 0.5 meters, okay? And the L here is going to be the thickness. And so the thickness was 0.1 centimeters, okay? Or 0.1 meters, which is 10 centimeters. Okay? And so we compute this. This is 2.5 meters, right? And so that's the shape factor for our planar wall. Okay. Okay. Right. So that's the walls. Okay. And so I think that's a nice kind of a nice kind of calculation to do, because then it shows that the that we can kind of directly connect the concepts of the shape factor and our thermal resistance. Okay. Now let's look at the edges. Okay, so for the edges of a box, this is actually in the table of the notes that I gave to you before. Okay, and so for the edge of the box, we have a formula from this. Okay, and so the formula for this, for the edge of a box, the shape factor is equal to 0.54 times D. Okay, where D here is the side length. Okay, and so we can go ahead and plug that in. And so we're going to have our side length here is 0.5 meters, and so our S is equal to 0.54 times D, which is 0.5 meters, and so that gives us 0.27 meters. Okay. All right, next we have the corners, and so the corners we have, this is going to be in the table as well. Okay. And so for corners, for the corner of a box, okay, the corner of the box is 0.15 L. Okay, where L is the thickness of the wall. Okay. Okay. And so we plug that in, we get 0.015 meters. Okay, so remember the thickness of the wall is 10 centimeters. Okay. Okay, so now that we have this information, so we have the shape factor for the edges, shape factor for the corners. Okay. And so our total shape factor here is going to be 6 times the wall shape factor plus 12 times the edge shape factor plus 8 times the corner shape factor. Okay. And so we add that all up, we get a total shape factor of 18.36 meters. Okay. Now that we have the total S, we can go ahead and plug it back into this equation right here. Okay, because we had the thermal conductivity and we had the temperature difference. Okay, and so our total Q here is going to be 18.36 multiplied by 1.04 multiplied by 0.450, or excuse me, by 450 degrees C, we get 8.592 kilowatts. All right, and so that's the that's 2D conduction. And so remember, the kind of the upshot for 2D conduction is you need to use the shape factors, and the shape factors you get from normally you get them from the table, but if you do see one of these on the exam, then I'm going to give you the formula for the shape factor. So you don't have to worry about writing in the table of shape factors into your sheet of notes. I just want you guys to know how to use them. Okay. All right, and so that's 2D conduction, and so that was the topic that was most voted on in the poll. Okay, so now we're going to go to the next topic, which is thermal circuits. Okay. All right, so thermal circuits is something that we've kind of been working with since almost the beginning of class, right? And so thermal circuits kind of leverages this idea that we can model heat transfer situations using electrical circuits. Okay. Okay. Where in particular, not just any electrical circuits, but just purely resistive circuits. Okay. And so we're going to look at cases where we use resistors to represent certain amounts of heat transfer situations. Okay. In particular, the idea of a thermal resistance is that whenever you have any kind of either material or a fluid or anything that can impede heat transfer, we can represent that like intuitively with a resistance. Okay. Okay. Because think of what resistors represent, think of what resistors represent for electrical circuits as well. Okay. And so, for electrical circuits, if you have a resistor in your circuit, it's going to impede the amount of current or the amount of electrical charge that goes through. Right. And so if don't try this at home, but if you took a battery and you connected the positive end of the battery directly with the wire to the negative end, then that's going to produce a current, and in fact, it's going to produce a lot of current because there's nothing impeding it, right? And so you just have a free flowing, free flow of electrical charge that goes along the wire. All right. And so heat is kind of the same way. And so heat will naturally want to travel, between high temperature locations to low temperature ones. But, and if it could, it would want to move, from the high temperature to the low temperature one at very, very high speeds. Okay. Okay. Right. And so if you have I'm just going to draw just an abstract picture, right? And so let's say that we have a kind of a nebulous thing here. Okay. And so this is hot. Okay. I have another nebulous thing here, which is cold. Okay. right? Heat always wants to go this way. So heat always wants to go from the hot, someplace hot to someplace cold, okay? And it wants to do this as quickly as possible, right? And so if it could, heat would want to move there instantaneously. So instantaneously, think of it like the meme of the guy that, the girl's walking by and the guy wants to hit on her, right? So the guy wants to go try to hit on her, but his friend's like, no, man, hold up a bit, okay? And so resistors kind of play that role of the friend that's like, let's slow down a bit here, pal, okay? And so instead of going directly through that, as quickly as possible, heat has to pass through matter, okay? And so, for now, we're not going to consider radiation. And so in order to go from a high temperature to low temperature, it has to pass through some kind of matter, okay? Okay. And that matter, whether it be a solid, whether it be a fluid, whether it be a contact resistance, right? That matter is going to impede the amount of heat transfer, okay? And it's going to cause it to slow down, okay? Okay. Right. Because remember, the way that conduction works is that it's basically a molecule to molecule exchange of energy, right? And so two adjacent molecules that might be right next to each other, they're going to exchange heat, and that's basically what conduction is. But there's limitations. There's limitations to how much energy one atom can pass to another one, or one molecule that can pass to another one, just based on the molecular structure of the material. Okay. And so because of that limitation, then those matters, or those layers that the heat must pass through, is going to impede its progress to some degree. Okay, and so it's not going to be instantaneous, but it's going to occur at a certain rate. Okay, and so thermal circuits are meant to capture this idea. Thermal circuits are meant to capture the fact that heat, when it passes through matter, there are some limitations and some roadblocks within the matter that cause it to slow down. Okay. And so how do we actually use these resistors in practice, or what situations we like to use them in practice? Okay. And so you could use a thermal circuit, usually for almost any situation when you're interested in temperatures at discrete locations. Okay. Okay. And so you've seen that a lot of times when we use thermal circuits, we use them to compute the temperature at a at a surface or a certain location. Okay, those thermal circuits work great for those. Thermal circuits also work really great when you have a situation where the heat is going to pass through several different layers of material. Okay. Okay. Right, because each layer of the material can be represented with a thermal circuit. And so this is a schematic that we saw in class. Okay. And so let's say that we have a situation where we have convection. Okay. On the left side. Okay, so we'll call this H1 T infinity 1. Okay. Okay, and on the other side, we have a fluid 2, so it's H2, T infinity 2, okay? Right. So this would be like material A, material B, material C, okay? And the thicknesses of all the material are given as the following. Okay. And so normally, if you wanted to solve for the temperatures at these locations, okay, so let's say that we want to compute the temperatures at each layer of the composite material, this would normally be really hard to do because you have 3 different materials as well as 2 convection type boundary conditions. Okay. But what we can do instead is that because these are kind of distinct layers of material, we can represent them with thermal resistances. Okay. And so instead, we can have a situation like this. Right? Where each of these resistors here would correspond to one of the situations above, right? And so for a convection type situation, we have 1 over H times A. Okay. For the conduction, we have LA over KA times A. For the second layer, we have LB divided by KB times A. We have LC divided by KC times A. And then for the final convection resistance, we have 1 over H2A. Okay. Okay. And so those are the situations when thermal circuits are good. Let's talk about how we actually use these in practice. Okay? And so the first thing that you should know about thermal circuits is how to use them to compute heat transfer rate. Okay. Okay, and so heat transfer rate from a thermal circuit, we're going to take Q, okay? Right. In short terms, the way that you compute Q here is you take the difference in temperature, delta T, divided by the total resistance in between them. Okay. So that's the formula that we have that's in the notes, but I do want to talk about some nuance behind this because that nuance kind of gives rise to a lot of the interesting thermal resistance problems that you might see, in the homework or the exam. Okay. And so I think a better way to list this formula, that's I think going to be more useful to you when you're doing problems, is you instead of delta T on top, you take the temperature at 0.1 or node 1. Okay. Node 1 in the circuit minus the temperature at node 2 in the circuit. Okay. Right. Next, you're going to divide by the total resistance, but the total resistance is not for the entire circuit. Okay. It might be if the nodes that you pick are the frontal node and the back node, but in particular, this R is going to be just the resistance in between the 2 nodes that you pick. Okay. All right. So what do I mean by that? And so basically, basically what this means is that you can choose any 2 points on the circuit. Okay, and you can use this formula to compute the heat transfer in between them. Okay, and so let's say, for instance, that we want to compute the heat transfer rate between this location here that I'm drawing with my stylus, okay, and this location right here. Okay, so we'll call this T1, and we'll call this T2. Okay. All right, and so if we were to compute the heat transfer rate between those two, we'd have T1 minus T2. Of course, assuming that T1 is bigger, and then we're going to divide this by only the resistance in between them. And so in between them, you can see we only have 2 resistances, which is the conduction resistance for layer B and the conduction resistance for layer C. Okay. So this is going to be LB divided by KBA plus LC divided by KCA. Okay. Right. And so that can work, between any two nodes. Okay. Another important nuance for this formula is that this Q, for all of our cases that we're only going to consider series circuits. Okay. This Q is going to be valid throughout the entire circuit. Okay. And so if we were to compute the Q between the endpoint here, the very end, and let's say that we between the very end and T2, okay, so it's T infinity 1, right? It would be the exact same Q. And so this Q would be equal to T infinity 1 minus T2, okay? Going in between those two, we pass over 4 resistances. And so we're going to have 1 over H1A plus LA over KAA plus LB over KBA plus LC over KCA. Okay. This Q is the same as that Q because it's just a single path, right? So there's only one way that the heat can go. And so if you take any 2 points in the circuit, they're going to share the same Q as any 2 other points in that circuit. Okay. We can leverage this information because we can use this in our problem-solving methodologies to compute temperatures at various locations. Okay. And so in particular, I'm thinking of the problem in homework 2, where I gave you the cylinder, which we're adding kind of constant layers on top of it. Okay. And so one common application for this is that you can use it to solve for the temperature at a certain node. Okay. Okay. All right, and so just for the sake of just so I don't just keep showing up again, let me draw another circuit here. Okay. The exact values of the resistances aren't going to matter, and so I'm going to call this R1, call it R2, R3, R4. Okay. Right. And so usually in these kinds of problems, you'll be given everything that you need to compute the resistances. And so R1, R2, R3, R4 are known. Okay. And always in these thermal circuit problems, you're going to be given at least two of the nodal temperatures in the problem as well. Okay. Okay. And so this problem might ask you, using this thermal circuit, what is the value of the temperature somewhere in the middle of the circuit? So let's call that T sub S. Okay. And so this is kind of exactly like the cylinder insulation problem that you got in homework 2. Okay. And so these types of problems kind of proceed in two steps. Okay. And so the first step is that you need to use the given 2 temperatures to compute the heat transfer rate throughout the whole circuit. Okay. Okay. Because those are given to you. And so you have to use what's given to you to compute what you're not given. Okay. And so for this, you're going to use your thermal, heat transfer equation for circuits. Okay. And so Q, in this case, since we're given T1, T2, will be T1 minus T2, okay, divided by all the resistances in between. Okay. And so since those two are the endpoints, then we just add up all the resistances in the middle of the circuit. Okay. So that's step one. And so step two, in step two, we leverage the fact that this Q is the same for the entire circuit. Okay. Okay. And so for instance, since we're interested in TS, let's take the difference between TS and T2. Okay. And so TS minus T2. Okay. We're going to divide this by the resistances in between them. And so in between them, we only have R3 and R4. Okay. This is equal to Q. Okay. But because this is a series circuit, right, this Q that we have here in the second formula is exactly the same as the Q that's up there. Okay. And so now that we've already computed the Q from up here, let's go ahead and plug that into this expression right here. Okay. And so by doing so, we'll have one equation that we can use to solve for the unknown coefficient. Okay. And so after plugging in for Q, this TS is the only unknown left here. Okay. All right. That's one common way that you can use thermal circuit problems. Okay. The other common way is the other common type of thermal circuit problem is what I like to call like an unknown resistance problem. Okay. Okay. And so in unknown resistance problems, what you need to solve for is some property of one of the resistances. Okay. And so I believe homework 1 had a problem like this, where we had the commercial oven design, right? And so in these types of problems, you're going to set up your thermal circuit. Okay. And so, let's use the same circuit as up there. Okay. And so you're going to have Q, okay, is equal to T1 minus T2, okay, divided by R1 plus, R2 plus, R3 plus, R4 plus, okay, or just R4, right? And so in these types of problems, what's usually missing or what's the unknown is some aspect of one of these resistors, okay? And so, let's say R3 represents a conduction resistance, okay? So this is L over Ka, okay? And so the problem might ask you to solve for, what's the thickness of this layer that's needed in order to achieve this, achieve this thermal conditions, okay? In these types of problems, the Q is usually going to be given to you. Okay. Of course, the temperatures are also going to be given to you. Okay. And all the other resistance values are also going to be given to you as well. Okay. And so what you need to do then is that you have one equation here, right, where both the things are going to be given are known. The only thing that's going to be unknown is one of the properties of the resistances. And so you're going to have to use some algebra here and rearrange some of the terms in order to isolate that one variable and solve for its value. Okay. And so if you want an example of this, you know, the commercial oven design of homework 1 was a good example of this. Okay, so I think in that one I asked you to solve for the convection coefficients of the air gaps, and so that's exactly kind of what this is. Okay, and so in those ones, you know, you couldn't compute the resistances of the air gaps, but you're given everything else in the problem, and so you can use all the other information in the problem to compute that convection coefficient for you. Okay, all right. And so that's kind of the two main categories of problems that you might see for thermal circuits in general. Okay, or I guess there's a third one. So the other one might just straight up just ask you, you know, what's the amount of heat transfer that's coming out of this circuit? And so in that case, you just plug this in here. Okay, but I did want to go over these two types of problems because these are they require kind of one extra step, and you know, these kinds of problems I get the most questions about, just because it's not just a plug into this equation, but you kind of have to use it in a little bit of a clever way in order to get what you're looking for. Okay, and with that, that's just about an hour, and so I'm gonna go ahead and call the review session here. Okay, so hopefully that was useful to you. And if you have any other questions on the exam, before the exam, please, don't hesitate to reach out, and I'll do my best to answer your questions. So best of luck studying, and I will see you all Monday.